Sure, this one for conditional probability and some stuff about Bayes' theorem for CS 262. Basic learning goals and outline. We're looking at the motivations, the review of joint probabilities, drawing some choice trees in Bayes' theorem. Let's jump right into the motivations. One limit that we ran into with first order predicate logic, or FOPL, which is also a limit of propositional logic, is that if you had something like P implies Q, or in first order logic, for all x, P of x implies Q of x, this has to be true 100% of the time. So what do we do if P of x implies Q of x only 75% of the time, or something other than 100% of the time? We don't have great ways to represent that, so this matters because consider the following situation. You want to classify email automatically as a spam message, some sort of terrible advertising message that's often a scam, or a ham message, a message you actually care about. Well, suppose you have 1,000 emails, and you've gone through and you've classified 800 of them as spam and 200 as ham, or legitimate email. So the basic probabilities here, the probability any message is spam is 0.8, and the probability that any message is ham is 0.2. This is a start, but it doesn't really get us where we want to go. We just have these overall probabilities. So maybe we can look at the individual words in the message to maybe get a better sense of whether it's spam or ham. So a lot of spam messages, for whatever reason, are about Viagra. Or pills, or some sort of free prescription drugs, or enlargements of various kinds, and so on. So suppose the word Viagra occurs in 600 of the 800 messages that we've classified as spam. Well, now we know the probability of the word Viagra occurring, given that the message is spam, is 0.75, and we would write that this way. Probability of Viagra, given that the message is spam, is 0.75. This is great, but this really isn't what we want. If what we're trying to do is build a program that can automatically classify whether a message is spam or ham, at least probabilistically accurately, what we really want to know is the probability that an unknown new message is spam, given that we know the word Viagra occurs in it, because we can have the program look through all the words that occur in the message. This is very different. The first one's easy, the probability of Viagra given that the message is spam, because that implies we've already classified all the messages. This is much harder. We don't know a priori if a message is spam. All we know is that the word Viagra occurs and maybe a bunch of other words, and we want to find a way to compute that and then combine the probabilities for all the words together. So we're going to focus on this first part today. Now, some other future uses for conditional probability. We just talked about spam classifiers. There's also medical false positives. We'll do some stuff about that sort of the next day in class. There's also what's called the Monty Hall paradox, which is another really awesome example of conditional probability. And these are really, really good things to know as an informed 21st century citizen. It's kind of part of the liberal arts education these days. You got to kind of be able to understand false positives for medical stuff particularly. So let's do a review of joint probabilities, because before we can talk about conditional probability, we really have to have a good understanding of joint probability. And if you've had a probability in statistics course, this shouldn't be too hard. If you haven't, go ahead and give it a try. You can go ahead and log into Moodle. These are the review questions for this lecture. Go ahead and pause me as necessary and answer these. So the first one, what are the chances that you roll a 2, or snake eyes, using 2 regular 6-sided dice? So you roll a total of 2. Go ahead and plug in your answer, and then go to the next slide, and I'll explain it. So did you say 1 in 36? If you did, then you're right. It is 1 in 36, and here's why. In order to roll snake eyes, what we're saying is the probability that you roll a 1 on both dice. So we sort of write this probability of rolling 1 and rolling a 1. Sometimes you'll see it written this way, probability of rolling 1, and then sort of using the and that we used from logic, and 1. Well, we know there's a 1 in 6 chance of rolling a 1 in the first die, and we know there's a 1 in 6 chance of rolling a 1 in the second die. These are independent events. What you roll on one die has no impact on what you roll on the other die. It's not like saying the probability that's raining in St. Louis and the probability that's raining in Chicago. Those are not necessarily independent events because there may be weather systems that commonly affect both Chicago and St. Louis, whereas when you're rolling dice, those are truly independent events. They don't have any impact on one another. And so, since it's 1 in 6 and 1 in 6, whenever you have a joint probability situation like this with independent events, you just go ahead and multiply, and so that's how we get 1 in 36. One thing I should mention, this is a 1 in 36 chance. If you do any gambling, which you shouldn't do because that's terrible, sometimes you'll hear about odds. A 1 in 36 chance, the odds of that happening are 35 to 1 because there's one chance it happens and 35 chances it doesn't happen. So this is sort of a little bit tricky because sometimes you'll hear, oh, well, you know, the odds are 35 to 1 that you won't roll a 2. That's true, and that means there's a 1 in 36 chance that you will roll the 2 or the snake eyes with your 2 dice. So let's do another one. Pocket aces. You're dealt 2 cards, and only 2 cards, from a shuffled deck of 52 standard playing cards. What are the chances you have 2 aces? So, you know, go ahead and pause me and flip over to Moodle and answer this. I won't be offended if you pause me. So did you come up with 1 in 13 times 17? If you did, you're correct. And let's talk about why. So there's 4 aces out of 52 cards. So the chance that you get an ace on the first card is 4 in 52, and if you do the division, that's 1 in 13. Now, once that first ace is dealt, once that first card is dealt, if it's an ace, now there's 3 aces left, and there's only 51 cards left. Well, 3 out of 51 is 1 in 17. So the chances of both of those events happening, it's 1 in 13 for the first one, and then if that happens, 1 in 17 for the second one. So that's where we get 1 in 13 times 17. So that's another joint probability question. So let's talk about more stuff about dice rolling. This is important for craps, which you shouldn't play because your odds of winning in craps are terrible, as we could go over in great detail now we're talking about dice. But this is also useful if you're playing Settlers of Catan. You want to know these things. So what are the chances that you roll a 6 with 2 6-sided dice? Go ahead and pause me, answer on Moodle. The answer here is 5 in 36. And let's go ahead and figure out why. There's 36 total possible dice rolls because there's 6 numbers that could come up in the first die, which are then combined with 6 total possible numbers in the second die. So there's 36 possible combinations. Let's count all the ones that add up to 6. We could roll a 1 on D1 and a 5 on D2. That adds up to 6. Or you could roll a 5 on D1 and a 1 on D2. Or you could roll 2, 4, 4, 2, or you could roll 3 and 3. You add all that up, that's 5 possible ways to get a 6 out of 36. So let's talk about bags of dice and some notes about notation. Bags of dice where you have questions like, suppose you have a bag of dice with these parameters and then you pull one out and roll it. What are the chances something happens? These are common joint and conditional probability questions, and so it's just some notes about notation. A 6-sided die is going to be called a D6. 12-sided die is a D10. 10-sided is 12-sided is D12. 10-sided is D10, and so on. 20-sided die is, of course, called really nerdy. I'm just kidding. It's called D20, and that's a Dungeons & Dragons joke from the 1980s, which I just had to put in here to remember my misspent youth from back in the day. So for the following several questions, suppose you have a bag with 6 dice in it. You have 3 D6s, a red one and 2 blue ones. We'll deal with the color of the dice later, but I'll just kind of lay this out. You have 1 D10, a blue one, and you have 2 D12, 1 red and 1 blue. So you have 6 total dice. 3 of them are D6s, 1's a D10, 2 are D12s. Now, you reach into the bag, you randomly grab a die and roll it. Well, what are the chances that you roll a 6? In other words, what's the overall probability of rolling a 6? Just by randomly grabbing one of these dice and then rolling it. So I'll go ahead and let you pop over to Moodle and answer this one. So did you come up with 1 in 12 plus 1 in 60 plus 1 in 36? If you did, you're correct, and here's why. Your chances of selecting a D6 are 1 in 2, right? Because there's 3 D6s and there's 6 total dice. So it's 1 in 2 you grab one of the D6s, and then once we know we've got a D6, it's 1 in 6. So using joint probability, this is 1/2 times 1/6. Now, it's also possible you grab the D10. There's a 1 in 6 chance you would do that because there's one D10 and there's 6 total dice. Once you have the D10, it's 1 in 10 that you would roll a 6. So that's 1/6 times 1/10. And then it's 1/3 that you grab a D12 because there's 2 of them out of 6. And then it's obviously 1 in 12 that you roll a 6. So that's 1/3 times 1/12. If we go ahead and sort of do out some fractional multiplication, this is what we end up with. If we add all of this up, it ends up, 23 out of 180, which is, I don't know, whatever fraction, whatever percentage it is. And if you note, once we sort of compute each of these joint probabilities, we're then adding them. And the reason we're sort of adding them together is, well, this is a joint probability situation. Once we know we've grabbed one of the D6s, we then know what the odds are that we roll a 6. But because there's sort of 3 possibilities here, we sort of compute the first one, and then the second one, the third one, then we add them all together because there's 3 possible ways to do this. Let's talk about drawing choice trees. This will kind of make this a little bit clearer. There's a 1 in 2 chance of picking one of the D6s because there's 3 of them, and then once we've done that, there's 1 in 6. It's sort of 1 in 6 to get the D10, and then it's 1 in 3 to get one of the D12s, and then we're computing the odds down here of rolling a 6. And then once we've done that for each subtree, we just go ahead and add them all together. So that's basically what we're doing here. So the colors of the dice, let's take that into account. So suppose we grab a random die. What are the chances that it's red? Go ahead and answer on Moodle. Great. If you came up with 1/3, you're correct. And here's why. Here's why. How many red dice are there? Well, there's 1 red one here, and there's 1 red one here, and there's a total of 6 dice, so it's 2 out of 6, or 1 in 3, that a randomly grabbed die out of this bag is red. Now let's talk about what are the chances of rolling a 6 with a red die. This is a joint probability question, but there's like an added layer of chance over what we've been doing previously. So this would be written probability of picking a red die and rolling a 6. And so we can take our probability tree and we can sort of split this out further. There's a 1 in 2 chance of picking a D6, but then there's a 2 in 3 chance down here of picking a blue one, and a 1/3 chance of picking a red one. 1 in 6 to get a D10, and then 1 in 1 of getting blue because there's only a blue one. 1/3 to get one of the D12s, and then it's half each for the red and the blue because there's 1 blue D12 and 1 red D12. So this sort of gets us this extra level of chance. So we want to know what are the chances of picking a red die and rolling a 6. Well, it's 1 in 2 to pick a D6. It's then 1/3 to pick red, and then 1/6 to roll a 6. 1 in 6 to pick a D10. 0 out of 1 to pick a red because there's only a blue one, so basically that reduces to 0. 1/3 to pick a D12. 1/2 to pick the red die, and then 1 in 12 to roll a 6. So we can kind of multiply all this out and add it up, and we get 1 in 24. So let's talk about Bayes' theorem. Everything we've done here, this has been a review of joint probabilities, but to talk about conditional probabilities, we need to kind of talk about, work our way up to Bayes' theorem. So let's start with conditional probabilities. A conditional probability question would be something like, what's the probability that the die was red, given that we already know we rolled a 6? So we'd write it this way: probability of that we picked a red die, given that we already know we rolled a 6. Now this is different than saying what's the probability that we picked a red die and we rolled a 6. That's a joint probability question. Probability the die was red, given that we already know we rolled a 6. This is a conditional probability question, and in fact, if you see given that, or given that already, or such that we already know, or something along those lines, often that means it's a conditional probability question. I think the most common phrasing is given that. So probability that the die was red, given that we rolled a 6, this is the same as the probability we rolled a 6 and the die was red, divided by the overall probability of rolling a 6. Now, luckily, we've already solved a number of these subproblems. We already know probability of rolling a 6 and picking a red die is 1 in 24, 3 in 72. We already know the overall probability of rolling a 6 is 23 out of 180, and if we grab our calculators and crunch out some numbers, we get about 0.326. Now, some intuitions here. Well, the probability of grabbing a red die and rolling a 6 is about, a little over 4%, 3 out of 72, or 1 in 24. And then the probability that the die was red, given that we already know we rolled a 6, this is about a third. This makes sense that the conditional probability is significantly higher than the joint probability, because if you think about it, the hard part is rolling the 6. Right, I mean, it's 1 in 6 on the d6s, it's 1 in 10 or 1 in 12 on the other dice, the odds are even worse. Here, for this conditional probability, we already know we rolled a d6. Now we're just checking to see what are the probabilities that it's red. Well, and given that there's only 3, the odds of choosing one of the red die overall is about a third. Now, the probabilities are a little bit different. You're more likely to roll a 6 on a d6 than on a d10 or a d12, and we know the die can't be red and also roll a 6 on a d10 because that die is only blue. So, but we figure this should be sort of close to a third, because once we know we rolled a 6, we're just checking the probability that the die was red, and there's, only 2 red dice out of 6 total, so intuitively, it makes sense that this probability is higher than this one, because up here, remember, this is a joint probability. Both events have to happen. The hard one is rolling the 6, so I just wanted to sort of talk about some of those intuitions. So Bayes' theorem, probability of A given B, this is the probability of A and B divided by the probability of B. This is the most general case. There's a lot of reading you could do on this. I think I've linked to some of it. About kind of the intuitions behind this and the history of it and so on, but I'm just going to kind of focus on the formula. So, probability of A given B is the probability of A and B divided by the probability of B. There's some algebra we can do here. Sometimes you may have a situation where, like, computing the probability of A and B is difficult or cumbersome, but it might be easy to compute the probability of B given A. Well, if you remember, if the probability of A given B is this, well, then the probability of B given A is going to be that. But the probability of A and B is exactly the same as the probability of B and A. Joint probability just can be switched. It doesn't really matter because you're just going to multiply them. So this means that the probability of A given B is actually equal to the probability of B given A times the probability of A, right? Because what we're doing is we're just sort of taking this, we're multiplying both sides by the probability of A, so now we can kind of solve for the probability of A and B. So this means the probability of A given B is actually the probability of B given A times the overall probability of A divided by the overall probability of B. Sometimes it may be easier to solve this form than it is to actually solve this form, because sometimes computing the probability of A and B might actually be difficult or tedious or something like that. Okay, moving on to the next one. Suppose you have a bag with 6 dice in it. What's the probability that you roll a 6 given that the die was red? Go ahead and plug this in on Moodle. So, did you come up with 1/8? There's, if you did, you're correct. There's sort of 2 ways to solve this. The first approach is to apply Bayes' theorem. We know the probability of rolling a 6 and picking a red die. It's 3 in 72 or 1 in 24. We know the overall probability of picking a red die is 1/3. We can sort of do some algebra, come up here with 1/8. That's one way to solve it. We could also just turn it into a joint probability problem. So we already know we've picked a red die, which means that there's one of the red d6s and one of the d12s. So half of the time we have a 1 in 6 chance, and half of the time we have a 1 in 12 chance. So we could actually solve it this way as well. So sometimes you actually can be a little bit clever about this. And we can't always do this for conditional probability, but for examples like this, we actually can. Let's do another one. So you got 6 dice. What's the probability the die was blue, given that we already know we rolled a 7? I'll give you a chance to kind of crank this out. You'll probably need to look at your little tree to figure this out. So did you come up with 11/16? If so, you're correct. Here's our table. And remember, what we're trying to figure out, probability blue, given that we already know we rolled a 7. What's awesome about this is we can't possibly have gone down this path because you can't roll a 7 with a blue die. So we can kind of crunch all of this out. Well, the probability, overall probability you rolled a 7, we can go ahead and compute that. Well, it's 1/2 times 0 for the d6s. It's 1/6 times 1/10 for the d10s, and it's 1/3 times 1/12 for the d12. So the overall probability of rolling a 7, this is what that looks like. Now the probability that we picked a blue die and we rolled a 7, well, it's 0 up here because you can't roll a 7 with a d6. And then we've got 1/6 times 1/10 for the blue d10, and we've got 1/6 times 1/12 for the blue d12. Remember, there's only one blue d12. The other one is red. So that comes up to 11/360ths, and what's fantastic, I wish I could say I magically knew to pick these numbers. This was kind of an accident. This comes out to 11/16 because we sort of do out the multiplication. Now, does the probability of blue, given that we rolled a 7, kind of fit our intuitions? Well, only 3 dice can roll a 7, the d10 and the 2 d12s. The d10's blue, and one of the d12s is blue, so 2/3 of the dice are blue. Now, the probabilities are a little bit different. I mean, we already know we've rolled the 7. It's a little bit more likely to roll a 7 on a d10 than on a d12, but we would kind of expect the odds to be sort of around 2/3. And in fact, 11/16 is fairly close to 2/3. So this kind of fits our intuition. Again, because we already know we rolled the 7, which was the hard part. Ooh, and I guess on that note, we are done.